Okay, so we want to start talking about greatest common factors, and this is a really important skill for us to have when we start our factoring. And to do this, we're going to start out actually talking about prime factors. So we're just going to take a little step back and remember what are prime factors. And prime factors, prime numbers rather, are numbers that have only themselves and 1 as factors. So if we, just start looking at numbers like, let's do the odd number. So if we look at 3, 3 is prime because it only has 3 and 1. 5 is prime, 7 is prime. Then we get to 9, and we see that 9 is again has factors of 1 and 9, but we also have 3 and 3. So 3 times 3 is 9. So as soon as you get to a number, or as soon as the number has another set of factors or multiple sets of other factors, you know that it can't be prime. So 9 is not prime, it's considered composite. And you don't really have to remember composite, it's just a term that we use. Now, when we start looking at this, I'm going to use, in the beginning, just our little factor tree. So if we have 15, and this will probably look familiar, I'm kind of doing it off to the side instead of down, but it means it's the same idea. What are the factors of 15? Well, the factors of 15 that we are familiar with are 3 and 5. And so our prime factorization, we see that 3 is prime and 5 is prime. So our prime factorization of 15 is 3 times 5. If we go ahead and do 18, now when we start talking about the factors of 18, some of you are going to think, that's 3 and 6, and some of you are going to think that's 2 and 9. And you're both correct, and it doesn't matter which one you choose, because that's not going to be done. So we look at it, and let's just say 2 and 9. We see that 2 is prime, only 1 and 2 will multiply together to get 2. 9, however, and we just talked about that, is 3 and 3, so we keep going. So the idea is that we keep going until we get to a place where we have all prime factors. So our prime factorization here is going to be all these terminal ends, so 2 times 3 times 3. So the prime factorization, again, 2 times 3 times 3. And you'll notice that all of these are prime. It's not a prime factorization until all your factors are prime. So let's go ahead and do 48. And again, we could do any number of things here. I'm just going to do 4 and 12 because that's what hits me. Neither of these are prime, so 4 is 2 times 2. 12, let's do 2 times 6. 6 is 2 times 3. So our prime factorization here is again going to be all the n bits, which is 2 times 2 times 2 times 2 times 3. Now we can restate this if we want to, 2, and we've got 1, 2, 3, 4 2s, so that's just right there, times 3. So, both of these are perfectly fine. The idea is just remembering what a prime factor is, because it's very helpful for us. Now let's take a look at this little guy. And this is obviously quite different. So what is the prime factorization of this? When you get to the variables, it's actually really easy, because when you get to variables, x cubed tells you that's x times x times x, and the y squared is y times y. And that's all there is to those. I mean, you don't really even have to think when you get to the variables, which is kind of nice. Now let's do 2 prime factorizations. We've got the prime factorization of 30, and I already did it, and the prime factorization of 45. So we did that, and if you're not, thinking of it, 30, let's say that's 5 times 6, and then that's 2 times 3, so that's where the 2 times 3 times 5 comes from. And then 45, let's say most of you are probably thinking 5 and 9. And 5 is prime, 9 is 3 times 3, and again that's where we get our prime factorizations. Now I've just kind of got them labeled out here, but I'm going to rewrite this. 30 is 2 times 3 times 5. And I know I'm going off long there, and there's a reason for it. 45 is, there was no 2, but there was a 3, and then there was another 3, and then a 5. And you'll notice that what I've done here is I put like stuff in a single line. So, you know, there's my like stuff, here's like stuff, and then the other ones are, there's only 1, there's no 2 in 45, so it's in its own column, and there's only 1 3, there's an extra 3 in 45 that isn't in 45 that isn't in 30, so that's where that comes from. So the next step that we're actually doing here is we're just sort of comparing things, and we're looking for things that are the same. Now we can do sort of a different version of this when we're dealing with fractions, but what we're doing now is we're looking for stuff that's the same. So in this case, we're bringing down the 3 and we're bringing down the 5. So we're looking for what's in common. Remember what we're talking about here is greatest common factor. So we're looking for what's in common. So we see that the 30 and the 45 both have a 3, a factor of 3, and both have a factor of 5. So now if we multiply those back together, we get 15. And 15 now is our greatest common factor of 30 and 45. And this is a very long way to do it, and sometimes you can see it, but the idea that we've got to be comfortable with first is that when we're finding things that are in common in numbers, it's going to take us a little work sometimes. So you just have to remember that sometimes you have to do a little bit of extra work. You may not have to, you may see it sometimes, but it's always worth it, because the greatest common factor, remember the key word there, well, one of the key words there is greatest, so it has to be the biggest thing, and it's really kind of a common error to find something that's not the greatest, to find a smaller thing. It happens with us when we work on fractions too, quite often. So now, when we're looking for the greatest common factor of polynomials, the first thing that we're going to do is write it in factored form. That's what we were just practicing. Then we're going to do what we do here. Sometimes you're going to, number 2 here, list each prime numbers that's a factor of the coefficients. Sometimes you can see it, sometimes you can't. And then when we start dealing with the variables, I'm going to talk about this a little bit, and then what we just did on the example that we just did there, 3 and 5, where we had the primes and we multiplied them back. So this is sort of the long version of what we're going to do. I'm going to show you some, maybe more simple ways to do it. So we're going to start with this nice example here. We want to find the greatest common factor. And what I've done here is I've just sort of taken each one out. You'll notice there's a negative there for some of them. And this 18 is, some of these exponents are missing, so I'm going to pop them in there. Don't know where they went, but easy enough to fix. M to the 5th. This is M to the 4th. Okay. That was a mistake when I set up. I don't know how I did that. All right, so now we're just going to do a prime factorization. Now when we look at 21, 21 is 3 times 7. And then M to the 7th, of course, is M times M. I'm just going to write it out. I have to count them. So 3, 4, 5, 6, 7. All right, there we go. Okay, negative 18. Well, we know we just did 18. So negative 18 is, we can put a negative out front or a negative 1. But it's also 2 times 3 times 3. And then 6 M's. 4, 5, 6. 45 is another number that we're familiar with. We just did that one. And that was 3 times 3 times 5. And 5 M's. I'm really trying to show you more about the variables here so we can get a shortcut going on that. And now negative 30 again with a negative 1, and then times 2, and 4m's. Okay, so the numbers are pretty straightforward. We see that we've got, let's get a different color here so it's easier to see. So we see that in the 21 we've only got a 3 and a 7, so there's my 3. Here I've got a 3, no 7. So we know that the biggest thing that we could have now is 3, because 7 isn't in everything. But there's a 3 here, and there's a 3 here. So we know that 3 is our numerical common factor. Now with the variables, this is one of those things where it can be really easy once you see it. So as soon as we see this, we see that we've got one m here, another m here that's in everything. You'll see that I've got them all sort of in a column, so it's like all kind of nice in a column. And then another one here. When we get to this fifth one, though, there is nothing here, so that's not going to work. So the only thing that we've got is 1, 2, 3, 4 m's. And the nicest short, so our GCF is 3m to the 4th. So the shortcut that I use when I'm doing variables is, when you're looking at, it has to be the same variable. And the shortcut is the smallest exponent. And I'm hoping some of you actually saw that. Smallest exponent will be your GCF. So you just, as long as it's all the same variable, it doesn't matter if there's multiple variables, you just do this for every single variable. On the same variable, pick the smallest exponent. All right. So we found that this is the little polynomial that we just did, and we said that our GCF was 3m to the 4th. Now that is the first step. The next step that we have to take is we have to divide it out. So we do a division. We take our polynomial and we divide it by our GCF. So we take, and hopefully you remember how to do this from last chapter, so we're just going to break it into pieces. Don't forget to bring the signs. And there we go. So now we've got it into the division, and now all we have to do is we're going to do the division. So again, nothing particularly new here. We're just sort of borrowing from things that we already know. So when we look at the first term, 21 divided by 3 is 7, and then we can use our shortcut. We've got the same variable. It's a division, so we subtract the exponent, so 7 minus 4 is 3. Again, a skill we learned in the last chapter. Bringing down the sign here, right? Now we do the second term. 18 divided by 3 is 6. Again, same variable, so we keep the variable and its division, so we subtract the exponents. Keeping the sign again, bringing it down. Divide the numbers. 45 divided by 3 is 15. When we divide exponents, we keep the variable, subtract the exponent. I'm going to put the 1 there. Remember, you don't need it. Here we've got the negative, so we pop that down again. Again, divide the numbers. 30 divided by 3 is 10. And then we've got m to the 4th over m to the 4th, and we can see that that cancels out. It's 1. All right, so now we've divided it out. So that's the next step. And then when we have looked for, or when we're looking for GCF, and we see here the proper form is to take the GCF, so that was 3m to the 4th, and in the parentheses we have the quotient of each term, or this, so we have 7 m to the third minus 6m squared plus 15m minus 10. And then we would think about how we could check this. So we've actually just done our first factoring. And the way we would check this is to multiply it back. And that would mean we would just take whatever the GCF is and distribute it back in the parentheses. If we get the same number back, if we take this and we distribute it in and we get back our original polynomial, we've done a really good job of factoring. Alright, so now we're going to try another one. And this little guy, we're going to do it a little bit shorter. We're going to see if we can figure out how to do this a little bit more quickly. When we look at the numbers, the first thing I see is a negative out front, so that means my GCF is going to have a negative. So that's sort of a key thing to remember. If you've got a negative out front, our GCF, put in the negative. Now we look at 12, and I'm picking 12 because 12 is the smallest number. And I can see I've got a 2 in there, 2 works in the other two numbers, I've got a 3 in there, 3 works in all of these numbers. And I can just keep going up if I want to. But the fact that I've got a 2 that works and a 3 that works means I can multiply those together and get 6. And now 6 goes into 12, 6 goes into 30, 6 goes into 18. So I'm picking 6 as my GCF. Now I look at the variable and I see that I've got the same variable. So I choose the smallest exponent. And there's my GCF quite quickly. So we see that our GCF is negative 6p squared. So the next thing that we have to do is do the division. Oops, better not go too far because I can't see that. So we do the division. We take our original polynomial, and we divide it by our GCF. When we do this division, again remember to be careful of your signs, we get 2p squared, negative negative, 5p, negative negative, 3, yep, I think I did something wrong with my, yep, this is supposed to be a 2, there we go, and p squared over p squared is 1, so that's gone. Right, so we did the division. Now we create the factored form, remember, by putting the GCF out front, so that's negative 6p squared, and in parentheses we put out the divided form, or we put in the divided form of what we just did. And of course if we want to check it, all we have to do is multiply it back. So we'll do a couple examples. This one, hopefully really quickly, we can see that we don't have a variable in both, and 3 is prime, and 3 does work in 12, so our GCF is 3. When we divide these by 3, we are left with m plus 4. So pretty quick and simple sometimes. Now when we look at this one, we say, all right, this is all variables. So here I've got an x, here I've got an x, here I've got an x, here I don't have an x. That means x can't be part of the GCF. Here I've got a y, a y, a y, and a y. So y is in the GCF. Then we look for the smallest exponent, and that smallest exponent is 3. And there we go. So now we're going to divide each of these by the GCF. And that's what's going to go in our parentheses. So x to the 7, y squared. Remember, we're subtracting the exponent because we're dividing. Plus x to the 6th, and of course I'm not doing anything to the x factors because there was nothing we could do to it. Y plus x to the 5th, and this y cubed, that's gone. And then of course the last one is y to the 10 minus 3 is 7. And we're done. So these don't need to take a lot of time, but you do need to do practice so you can get really good at them. We're going to do just a few more examples. You may want to go ahead and pause and then try these on your own, and then come back and turn the video back on to see how you did. So we're going to look at the first one, and we're looking for our GCF. We see that 2 works here, it works here, but it doesn't work here. My inclination, by the way, is always to try the smallest, or to work with the smallest coefficient. It just goes more quickly. So if we look at 2 and we know that it doesn't work because it doesn't work for 15, then we look at 5. 5 works in 20, 5 works in 15, so 5 is the number that we're looking for. Obviously m, smallest exponent, and there's our GCF. Now we divide it out, and I'm going to keep writing this written out this way. Many of you will start not needing to see this, but for those of you who do, I'm going to keep writing it. So 20 divided by 5 is 4. M to the 5th divided by m cubed is m squared. Bring that sign. 10 divided by 5 is 2. M to the 1 plus 3 m cubed over m cubed, of course, is 1, so it's gone. And that's our first little example. Let's do another one. This one is a little bit more complex, so this is kind of nice. Again, here's our smallest number right here. So 5, pretty easy. 5 goes into everything, so we know that it's 5. We can see that there is an x in each of these terms. The smallest exponent is 6. We can see that there is a y in each of these terms. The smallest exponent is 2. So there's our GCF. Now we go back and we divide each of these. By the GCF. So when we divide the first term, let's go ahead and change the color so we can see it. So when we divide the first term, that plus should be not in there, but that's okay. We have 5 over 5 is 1, so that's gone. X to the 8th divided by x to the 6th is x squared. And y squared over y squared is 1, so that's gone. Bring the sign that I accidentally put in that circle, plus. And then 30 divided by 5 is 6. Y to the 7th divided by y to the 6th, x to the 7th divided by x to the 6th. Y to the 3rd divided by y squared. Bring in that sign here. 45 divided by 5 is 9. X to the 6th over x to the 6th is 1, so that's gone. Y to the 4th divided by y squared is y squared. And there we have it in factored form. And the last couple examples, let's go ahead and look at the number here. We can see that there's a 7 factor in each of these. 7 is kind of an easy one to see on that. And then of course m. And we see that the smallest exponent, we don't see the exponent, but we know that it's 1, so it's m to the 1. So we're going to divide each of these by 7m. So 7m to the 5th divided by 7m, m to the 4th, plus 2, 14 divided by 7, and then m cubed divided by m is m squared. And then plus, we've got 7m over 7m, so that's exactly the same, so that's 1. You've got to be really careful with these. The inclination sometimes is for students to leave those out when you're just learning this, and you've got to remember, you know, that sort of thing. Any number over itself, we learn that in fractions. Any number over itself is 1. We need the 1. And we need the 1 because when we multiply it back, remember, we have to come back with exactly the same thing that we started with. And if you leave out that 1, you'll be missing that 7m at the very end there. So go ahead and try this next one. and then when you are done, go ahead and start the video again. So let's go ahead and look at this now. We've got, again, I'm looking for the simplest coefficient, and we've got 21, and then we get to 7. And I'm very happy when I see numbers like 7, because it's a simple number, it's a prime number. So now all I have to do is see, does 7 go into everything? And 7 does go into 21, it does go into 49, it does go into 14, it does go into 7. So 7 is our numerical GCF. Now we're going to look for the variable GCF, and we're looking to see if we have one. So we've got a y in each term. So y is definitely part of our GCF. And then we look for the smallest exponent, and that's 2. So there's our GCF. And now we're going to divide each of these by 7y squared. So when we divide our first term, we get 3y to the 8th plus 7 over 7 is 1. Y 8 divided by y squared is y to the 6th plus 49 divided by 7 is 7, y to the 4th. 14 divided by 7 is 2, y squared. And then 7y squared divided by 7y squared. Again, the idea of making sure that you don't forget that 1. Sorry for how messy this looks, but I had a different one in there, and I decided I forgot to do a certain type of problem, so I wanted to get one in. When we look at this again, we're looking for a GCF, so we look at the 3. We know 3 is prime. So 3 does not go into 4. So again, 3 doesn't go into 5 because 5 is prime. So what happens if we have these coefficients and they don't have anything in common? And the answer is it's not that big a deal. We just now move. We know that the number isn't part of the greatest common factor. We see that there's an x in each term, so we can say that there's definitely an x, and then we just look for the smallest exponent. So x squared is our entire GCF, and now we just divide out each of these by x squared, and we're left with 3 plus 4x minus 5x to the 5th. And we're good to go. So then you just, again, to check, multiply back. Now this is sort of forever and for always. When you start any factoring problem, the first thing you do is look for a GCF, and if you have one, you need to factor it out. I'm sorry for the length of this video. I know I went way over my limit, but I just wanted to get them all in. You're certainly welcome to sort of stop and start as you need on any of the videos.